Section 11.2 is dealing with the chi-square test for two-way tables. We're going to learn two hypothesis tests in this section, but they're going to be pretty similar. Two sample Z procedures allow us to compare a proportion from two populations together. We got a group of guys and a group of girls, and we're comparing the percentage of Democrats in this group to the percentage of guys that are Democrat. Two populations comparing one percentage. Goodness of fit allows us to compare the distribution of a categorical variable. So now we can talk about more than just one percentage, but rather an entire distribution. But it's really just for one population, and it's comparing to a claim distribution. None of these procedures allow us to compare the distribution of a categorical variable with many outputs across multiple populations, maybe two or even more. So there's a need for that, and the test that does it is going to be chi-squared test for homogeneity. All right, so this first part is just a review from Chapter 1. Developer at Riot Games is interested in the age demographic of their popular game League of Legends and how it compares to its competitor Dota 2. They take a random sample of 100 users and from each game and record their age. Compare the distributions. So we have Dota 2 versus League of Legends, and then we have less than 25 age group. We got 25 to 40 age group, and we got 41 plus. So let's calculate the percentage and make a little table here, I guess, and try to organize our information, right? So this is 30 people out of 100, or 30%. This is 40 out of 100, or 40%. And I am showing my work here for a reason. We're getting ready for this AP test. They expect you to always show your work whenever you do even ridiculously easy calculations like this. So let's do it. Anytime you do something, write down how you got it. Picked easy numbers here, so this would be quicker. So as you can see, so for young players, Dota was at 30%, whereas League of Legends was at 50, and then 40-30 and 30-20. Looks like League of Legends has a younger player base, and Dota has perhaps an older player base. Let's make an appropriate graphical display. You could do probably a couple different ones. I'm going to do a stacked bar graph. So this is 100%, 50%, 75, 25, and then we got League of Legends, Dota 2. And these are both going to go up to 100% because we're taking the percentage of the whole. And then we're going to segment it off for the different age brackets. So for League of Legends, half of them were young. So this is going to be 25 and under. For this one, it was about 30%. So you can see there's a difference. Let's go to the top and do the top. League of Legends 20%, so it's just right here. This one was 30%, so a little bit more. This would be the old timers, 41 plus. And then in the middle we have our middle-aged, 25 to 40. Label, game, percent, title, segmented bar graph of, I don't want to put down the title, I'm wasting time. So as you can see, the percentage seemed to be different. Now when we talked about this earlier in the year, we talked about whether there was an association or a relationship, or if the distributions are simply the same or different. And we're kind of asking the same question here. It's just now, though, we got to remember that this is a sample from a population. So yeah, even if the populations were the same, you'd expect there to be some differences in these percentages. The question is, are the differences bigger than what would be observed due to random chance sampling? Or are the differences significant? Are they big enough so that it's maybe not due to random sampling? All right, so let's set this up here. If the distributions of game choice were exactly the same for each age group, then what would be the expected counts of each cell? So if these distributions were the same, okay, so I wish this was a little bit, these are both 100, so it kind of trivializes this because that means these are always going to be the same. 100 and 100, so these are going to basically just split these in half, 40 and 40, 35, 35, 25, 25. So that's not real interesting. That's pretty easy to see. I kind of want to just get you thinking about how you would calculate these if they weren't the same. So could we just, for the sake of argument here, just kind of pretend maybe that this is 200 and this is 300. These would simply be different. But let's just, I just want to talk about how to get this cell right here. How do you get this cell whenever you have different size things or whatever? And we talked about this at length in class a little bit, but basically these 80 people have to be distributed in this ratio, right? Like however many people here, this has got to have twice as many people as what's there. So we want this ratio over here. So how could we do that? Well, I guess I could find out what percentage of people play League of Legends. Well, League of Legends is played by 200 people out of the 300 people. That's the percentage that play League of Legends. And then of the total 80 that play League of Legends, you'd expect it to be this in this ratio. So let's just multiply that by 80. That would give it to you. Or you could look at it another way. You could say, well, 80 out of 300 people are young. That's the ratio of young people to old to everybody. Well, the League of Legends players have to have, these 200 League of Legends players have to have that same ratio. So if you just take this percentage times 200, you'd get the expected counts. So no matter which way we look at this, we can see that in order to calculate this, you're basically taking the product of your column total times your row total, and you're dividing it by your grand total. Column total, row total, grand total. So that's how you get these expected counts if it wasn't easy like this example. Okay, now this example was just that, and that's fine. These are our expected counts. But in general, the formula for calculating expected counts is your row total times your grand total, row total times your columns total divided by your grand total. So this is what you would expect. These are what's observed. These are what's expected. So just like our chi-squared test before, we're going to use this chi-squared test statistic. I forgot my summation here. You're going to take the difference between your observed and your expected squared over your expected. You're going to sum it up for all 6 cells, right? And calculate that chi-squared test statistic. Now the degrees of freedom is going to be slightly different. It's still the number of outcomes from one categorical variable minus 1, but because it's a two-way table, we're also going to do the other variable minus 1, number of responses minus 1, and it's the product of those two. So it's basically columns minus 1 times rows minus 1. So this would be a 3 minus 1, which is a 2, by 2 minus 1, which is a 1. So this would be a 2 degrees of freedom. And then the p-value is simply going to be the area to the right of your chi-squared value, as it was before. Conditions for the test are kind of the same. Random, 10%. Each sample needs to be random. Each sample needs to pass a 10% condition. All expected counts need to be greater than or equal to 5, and your samples need to be independent of each other. We got 2 samples from 2 populations in this. So we got to go back to those multiple samples conditions, okay? Unless it's an experiment. If it's an experiment, then we're going to skip those 2, right? Just like before. So a lot of the same stuff as before. All right, so let's actually run through a test at 9 minutes. Let's do this on the next video.